Welcome AC circuit students. In this demo video, I'll be reviewing some ways that we can use our Picoscope USB oscilloscope or any other oscilloscope and function generator, and a little bit of internet Googling to identify transformers that you might run across. So as a quick review, a transformer is basically two inductors coupled with either air or some kind of ferromagnetic material that contains the magnetic field produced by both inductors, such that the magnetic field of one inductor is the same as the other. And so we can achieve magnetic as opposed to electrical connection of energy between the two inductors. That allows us to do useful things like step voltage up and down, as well as energetically connect but electrically isolate components in a circuit. So as it turns out, I was looking for an inductor and a transformer both to do some experiments, and I ran across this beautiful little proto board equipable transformer in my kit that it was given to me by a friend. All I had were the markings on it, and in fact it said TM013-R on one side, and it looked exactly like this. And the nice thing about it is it had little leads that could plug right into my proto board. And since I like to use my proto board to keep my experiments as neat as possible, I thought, wow, this could really serve me well. I needed a couple of high-value inductors and I needed a transformer. But the problem is I had no idea how to use it because I didn't know what the step-up, step-down ratio was, nor did I have any idea which leads were the primary. There's 6 leads. I didn't know if they were center tapped or what was going on, because even though, it was probably likely that one side was the primary and one side was the secondary, and typically the middle connection is a center tap in most transformers. That's not always a guarantee, and that's especially true of small components that might be ready to fit onto your proto board. So my first task in trying to identify how to use my transformer was to do a little research, and of course this led me to several different websites that showed this product manufacturer's name, and this particular one that I'm sharing with you is a music electronics outlet, Bonsai Music, one of many. So this alerted me to the fact that this was an audio transformer, so it's meant for small signals. This isn't something intended to power your house. And it included a little bit of information and basically an idea of what the thing looked like. So I'm going to go ahead and share with you the picture, because rather than using my web camera, I'm just going to point to the features on this picture that correlate with what I saw. So unfortunately there weren't any data sheets necessarily available here. I could ask questions. This included something that looked like the product name, but there was no pinout guide to tell me what was the primary and secondary side and what leads might be connected to what. So I was kind of left to my own devices there. So the first thing I remembered about transformers is that typically the side that is intended to be the high voltage side, given that power through each coil of the inductor, each set of windings, is equal, the high voltage side is going to have lower current and vice versa, which means that in the absence of a big difference in number of windings, there might be something that I could infer based on the resistance from one lead to another. Furthermore, I might be able to use just continuity to identify which of these leads correspond to which winding and is the transformer isolated or not. And I'm gonna attempt to use this nice 3D view to show what I did. So you can see we have 6 leads. So the first thing I did was try to figure out which of these leads was electrically continuous with the other. So I used my digital multimeter, and I noticed that each of the 3 leads on each side were all continuous with each other, but were isolated from any of the leads on the other side. So the first thing that told me is this is an isolation transformer, so there's, as opposed to an auto transformer. So I have 2 sets of windings that are electrically isolated, connected with a magnetic field. And the next thing I noticed is all 3 of each of the leads on each side were connected with each other. So that made me think, okay, we probably have 2 ends of a winding and very likely a center tap. So as it turns out, the side that says P, which I thought, maybe that's primary. You know, basically the side that one would normally put power into as a default. Of course, we could use either side of a transformer winding as a primary, depending on whether we wanted to step something up or down. But in many transformers that are used for ordinary applications, someone intends to step, say, line voltage down from nominal 120 volts to something more usable. So in those cases, the primary would tend to be the high voltage, low current side. So I would have expected, all other things being equal, to have that side of the winding, you know, have a greater number of windings, but also have a smaller gauge wire. So that combination, more windings, means a longer coil of wire in the primary inductor side, and then maybe not as large of a diameter of wire or a larger gauge wire. Both of those are going to lead to a much higher net resistance across the primary side. So at this point, I measured the resistance from this lead to this lead and got about 77 ohms, which is a reasonable amount. That would indicate a fairly large inductor. Furthermore, I noticed that the resistance from the middle lead to either one of the end leads was almost exactly half of the 77. It was about 38, 39 ohms. That combination of information led me to believe that this was a center tapped winding. So now I know, right now I have the choice of using all the windings or half. So I've already got a bit of versatility now in how I would use that transformer, or use it as a standalone inductor. Okay, going to the other side, when I measured from basically the one outer lead to another outer lead, I got a resistance of 1 ohm, almost the sort of the limit of what my meter could measure, and I got about 0.6 from the middle lead to either one of the other 2. So that was a very good indicator, first, that is indeed the stepped down, the low voltage side, because it's either got fewer windings and or it's got a larger diameter wire, smaller gauge wire to handle what would be the larger amount of current. P equals IV, lower V, higher I. And again, the fact that we had, that I measured almost exactly half the resistance between the middle lead and either of the other 2 would be a pretty good indication that I have a center tap on that side. So my conclusion was that I had a high voltage side where the little transformer was marked with a P, and by the way, mine looks almost exactly like this. And then I had a low voltage side on the blank side, and that the middle lead actually did correspond to a center tap, or the middle of the winding, splitting the number of windings on each side neatly in half. So at this point, the only thing I don't know about the transformer is the ratio. So what is the actual step up or step down ratio? And I also don't know what the actual inductance is. So of course, remember, you can always use a transformer one winding as a standalone inductor if you need to do so. So I'm going to move ahead to my Picoscope and give a little demo of how I went ahead and measured the step up or step down ratio. So I plugged the nice transformer into my protoboard, and the side that corresponds to P, I fed with a sinusoidal voltage signal. Here's 60 hertz from my arbitrary waveform generator of my Picoscope, and I delivered that signal across the full what's marked as P for primary winding. So I didn't use the center tap. I applied it across all the coils, all the windings of that side of the inductor, and then I collected signal A across that same winding. So basically I'm measuring my as delivered signal to what I'm assuming is the high voltage side, and then channel B is measuring across what I'm assuming is the low voltage, we'll call it the secondary side in this case. And I want to make an extra note that knowing that this is an isolation transformer, I went ahead and used the alligator clip of channel B, which I just wiggled, just showing kind of how sensitive it is to little signals here. Because I have it, I'm not delivering a signal, so it's just kind of picking up whatever's waving through the air. What I'm doing is I'm establishing a common ground on either side. And by the way, the signal you're seeing is, let's go ahead and turn these off. That is literal noise through the air and possibly something coming from my headset. This gives you an idea of how sensitive your scope leads are. So with an isolation transformer, we don't have a common point in the circuit that we would reference to our Picoscope ground. So I basically said one side of both coils of that isolation transformer I've now put at the same potential rather than letting it float. So I'm measuring across based on a common voltage. So I'm going to go ahead and turn my signal on, and I'm going to start by auto scaling my my signal A. I'm going to add an auto trigger to keep my display still, and I can use the rulers to measure about 605.6 millivolts. I'm asking for a nominal 1 volt, so that is a significant amount of sag for my Picoscope. But of course, I am putting this signal across something that has a nominal 77 ohms. That's not a lot of ohms. And at 60 hertz, I know that I don't have a lot of inductive reactance. I would probably see a lot more reactive impedance if I went to a higher voltage, and so my as measured amplitude would be much, much closer to my, I asked for 1 volt from my AWG, so I'm seeing some sag. So I'm going to reference everything to this, this about 606 millivolt amplitude, we'll call it high voltage side. So now I'm going to go ahead and turn on my lower voltage side. And I'm noticing that I'm getting a tremendous amount of noise that I wasn't getting before. Okay, so I'm going to readjust my leads a little bit. There we go, we're a little better. And I'll make a note that I am oversampling. I'm using that resolution and enhancement feature that the Picoscope gives me, and instead of using the default 8 bits, I'm using 9 bits, and this is giving me a little bit smoother curve, so I can make a measurement with the rulers a little easier. So first thing to notice is that my B, channel B, which is measuring what I assumed was a low voltage side, it's at a scale of 100 millivolts as opposed to 1 volt for what I thought was the high voltage side. So I guessed right there. I definitely, the side marked P is indeed the high voltage side, so chances are this little transformer was intended to take something closer to line voltage and step it down to a low voltage appropriate for use in another circuit. So I can just basically measure peak height to peak height on my sinusoidal signals, and so I can see that my voltage amplitude for my secondary, my low voltage side, secondary in this case, primary and secondary are relative to what you're putting in and what you're getting out. So I could basically say I have 606 millivolts divided by 50 millivolts, and that gives me something on the order of 12. So I would assume that based on that measurement that I have a 12 times step down transformer. So the number of windings on the primary or the high voltage side, it's 12 times whatever is on the low voltage side. So that's a 12x step down. Now, of course, if I turned it around, and applied my voltage signal to the secondary or to the low voltage side, it would be functioning as a step up. So there's a 12x difference in the voltage that I would get from one side of this to the other. The other thing that is important, and I'll go back to the picture, I've basically deployed the positive side of my my signal lead literally to this leg, to this lead on the transformer, and I'm measuring the signal, positive signal, with my scope leads to this leg and then this leg respectively. So I'm kind of measuring the same physical end of the transformer as being, you know, the de facto positive side, or the side I'm measuring with my lead. That measurement physical location is giving me my primary and secondary waveforms out of phase. So that's giving me an idea of basically which polarity the transformer is. If I wanted these to be in phase, if I wanted to get basically my secondary to be going the other way, I would just simply swap the leads. So that's the other important thing. Now, last but not least, I can explore that idea of the secondary. So I'm as we speak live, moving my probe B scope lead to that middle lead on the transformer, and I'm doing it live, and it's telling me it has lots of noise and doesn't like that very well. So that's a little bit artifactual. But that said, let's go ahead and do an auto setup. Sometimes that helps the scope. Nope, this is a real problem with the signal. We're looking at some real noise. So I wouldn't put too much verity in that. That's a very distorted signal. So it's a combination of a lot of things other than just the sine wave that's being brought over through the magnetic field. But nonetheless, we can get a little bit of an idea of what the amplitude of this crazy signal is, and it is indeed about half of what we had before. So that gives us an idea that our suspicions that that center tap lead was probably truly a center tap. And so now we've gone back to the full winding on the secondary side. So last but not least, we can, and I'm going to turn my Picoscope off. While I do this, I can go ahead and do the same thing for the high voltage side. Now I'm going to energize between the center tap and the lower, the other end, the negative end, so to speak, and turn my signal back on. And so now we have a 500 millivolt full scale on our signal A. So 221.8, and we have a 50 millivolt signal on our B, so 34. So we'll see. I mean, theoretically, one would hope that this would give us a ratio of about 6. 35 divides 6.3. So now we have our distorted signal again. So now, having applied my input signal between what I suspected was the center tap and one end of my primary or my high voltage side, now I only have a step down ratio of 6. So I kind of have 4 different ways that I can go. I can either apply full winding on my high voltage side or half, and then full or half on my secondary. So I can get many different combinations, and of course I can flip it around. I can apply my signal to the low voltage, the fewer winding side, and then take off a higher signal at lower current. So I am now confident that I am ready to use my little gift transformer to step my voltage up or down approximately 6 or 12 times. And I'm confident that I know where the center tap is, what the transformer polarity is, and I can probably, with some amount of confidence, use the information from this website to get an idea of what the power capabilities are. If I'm powering this with my Picoscope, Given that the Picoscope has negligible current output, I don't have to worry about power dissipation, but if I were to use something with higher current output in the form of a supply, I would want to know what my total power capabilities, power dissipation, because I would have to worry about how much current I'm flowing through the wires of that winding. So the only thing I haven't done, which would be an exercise for another video, of course, I personally don't have too many very large inductors in my kit, and I found several times that I could use one to get a higher inductive reactance in some experiments. So something else that I could do is go back and put one side, either the full winding or half, together with a capacitor and use the phenomena of resonance to see what the actual inductive reactance is at resonance, and then use the frequency to get an idea of what the net inductance of a full or a half winding on either side of the transformer is. So that's the only thing I have not done to make full use of my nice small audio gift transformer. So hopefully this gives you some insight in what to do if you find yourself in need of a transformer and you have access to one and aren't quite sure how to use it. This is a little bit of a good guide in how to make use of something. First, find any markings, Google it. Chances are there's going to be some information and even maybe a manufacturer's full data sheet. 2, find the pinouts, see what they correspond to in terms of high voltage side, low voltage side windings, whether or not you have center taps or intermediate taps, and whether or not the transformer is isolated or auto, where the windings are or are not an electrical contact. And then last but not least, go ahead and use your oscilloscope, deliver a signal, and get your step up or step down ratio. Thanks so much, and have fun with your transformers.